whenever you two are ready, could you explain what you built?
Yeah, so we have a gas particle simulator where we currently have 100 particles on the screen with a box size of 100 by 100 pixels. And we are basically looking at the particles interacting with each other, and we kind of also look at the pressure, volume, number of particles, and temperature, where pressure is the number of collisions with the walls, volume is the size of the box, number of particles is number of particles, and temperature is the speed of each particle in terms of pixels. Yeah, and we can step through our state machine and how we initialize the X and Y values for each particle. So we use an LFSR, linear feedback shift register, which outputs a random value of 13 bits. And we initially, in order to get the particles to stay inside the box, because we needed to initialize them inside the box, we modded the numbers to get inside the box, but then we realized that used a lot of resources, so we decided to mask that instead.
Okay.
And that's how we initialized the X and Y, and also velocities, because we kept the movement of particles in only the X and Y axes, so we needed the velocity to be either positive or negative or zero in both X and Y direction.
Okay.
And then do you want to talk about either clear screen or erasing? Or...
Okay, yeah. So essentially, each time we run through the simulation, each time step we update the position and the velocity of each particle. And so the box only gets redrawn upon reset, but then each time the particle gets a new position, we have to erase the previous position of the particle.
1 second. Can you guys keep it down just slightly? We're going to do a demo. Okay, go ahead.
We print the new position of the particle, and we update and we erase the old position of the particle. And all of this updating is done sequentially, just with one particle update register. Since time wasn't an issue, we realized we could just update each particle sequentially, and so each module, or the one module, can be used for all of the particles by changing the particle or the wire, changing what the wires of the module are connected to in terms of like which particle.
Do you want to talk about the module having the wall collision as well?
Oh yeah, so also the module, since it detects collisions with the walls just because we need to determine if the velocity is reversed in terms of determining the new position. So when we do that, we also just mark if there was a collision with the wall, and this helps us with pressure calculations that we're going to talk about later with the command line interface. And then we cycle through like 1,000 time steps of the 1,000 time steps of each like update of like every single particle, and we count the number of wall collisions in that 1,000 time step frame.
We use that to kind of represent pressure. And when we're checking for collisions between the particles itself, as Sarah mentioned, we didn't have an issue with meeting timing, so we decided to just, for each particle, check every other single particle for their X and Y positions, which isn't the most efficient, but we didn't have an issue with timing, so that was fine. And we would determine the next direction to maintain momentum with whichever direction it was coming at, and it wasn't too bad because there were only 16 possibilities based on which direction each particle was going, since it only travels in 2 axes, and this is the HBP collision model. Yeah. And then after updating their X velocities, we would draw the new pixel and wait and repeat.
Okay.
So that's pretty much what happens on the FPGA.
So each particle only moves horizontally or vertically?
Yeah.
And if it hits a wall, you reverse its velocity. And then, can you just clarify what happens in the event of a particle-particle collision?
It'll determine based on whatever direction each particle is going at, the direction it'll go at, it'll reverse. So we set all 16 combinations based on the HBP collision model. Yeah.
Okay. And then you're getting a measure of the pressure by counting the collisions with the wall.
Yeah.
Just sort of your measure of pressure.
To get like an average, we measured it over a few time steps.
Okay. And then your measure of temperature is the speed of the particles. And then volume, of course, is the area of the enclosing square.
In our case, we did just like one side, but same thing.
Okay. Okay. Great. Great. Cool.
Yeah, and then we have a bunch of parameters being sent or values being sent to the HPS over PIO ports, and one of which includes these switches that keep two variables the same. So since we have 4 parameters in this demo, we want to keep 2 parameters the constant, and then have the other 2. One would be one that we adjust, one that we change and we set explicitly, and the other would adjust accordingly to keep the other 2 constant. So we can see that here, where we can print the current values for all the parameters. So we have the pressure being 217 wall collisions. The volume of the box is one side, which is 100 pixels. Number of particles is 100, and the temperature, which is the particle speed, is 2 pixels per time step. And we can set 2 parameters to be constant or to change right now. So right now, volume and temperature, we want to change volume and temperature, and number of particles and pressure will stay the same. So if we click here and change the parameters, it'll ask if you want to change volume or temperature as specified with the switches. And if I want to change temperature, I know what scale it is because we printed it earlier, so I can increase the temperature by pressing 3 and the pixels will move. It'll reset and clear everything and actually it'll update on the fly for speed. It'll change the temperature to 3 and then update.
Okay.
And it'll print out the pressure goal, which is just the pressure that it was initially, and it'll take some time to update the pressure because it needs to wait for that average pressure before adjusting what the volume is based on what the new pressure is compared to our pressure goal. And then it'll keep doing this until it reaches the pressure goal. So it's decreasing slowly as the volume increases.
The volume's increasing here. So we're seeing something like there it just increased again. We're seeing something like a visualization of like the ideal gas law.
Yeah.
So you held, what did you hold constant here? You held constant.
Number of particles and pressure.
And then you increased the temperature.
Yes.
And so as a consequence, we saw the volume increase.
So that the pressure, because with the increase in temperature, the pressure would increase because there are more collisions with the wall, and we want to lower that pressure, and number of particles stay the same because we set that, but we want pressure to lower once again to match what it was previously, so it slowly increases the volume or the box size, and then now we have reached a pressure of 191, and we're trying to achieve 199, and we kept like a buffer.
Sure.
So that's one combinations, and we have combinations for PV and PV.
All the other ones.
Yeah.
Cool.
Yeah.
I think that did you want to show the oscillation one?
Oh yeah, there would be some times where if we change the parameter, for example, for volume, if we right now we're at 100, if we want to make it 120, it'll change the temperature, but it's really sensitive to the pressure is sensitive to temperature change, just because it has jumps in the collisions. So it'll oscillate between 2 because it can't reach that exact pressure goal because the temperature, one step of a change in temperature will drastically change the pressure. So we set a oscillation counter to make sure it doesn't oscillate for too long, or else it'll oscillates forever.
So it increases its temperature, which exceeds its desired
Yeah.
pressure.
And
So
it'll
it decreases
And then-
it,
yeah,
and
and
then
then-
that drops it below.
Low.
Yeah.
Yeah, it's not within like the 10 above or below range.
Yeah.
So we just make sure if it oscillates twice, then we just assume that it's going to oscillate forever.
Sure.
And then we just cut out, and then you can change whatever other parameters you want to change.
Yeah. That's it.
So this, how many particles is this?
This currently is 100 particles, and I believe it can go up to 200, but we kept it to 150 just to be safe.
Sure.
Yeah.
Okay.
And we were limited by our logic, just because we had a lot of checks. Yeah.
So that was your limiting resource. Okay. And then can you just clarify? So, what are the responsibilities of the FPGA here, and then what are the responsibilities of the HPS?
The HPS kind of only doesn't do much. It kind of prints all of this, and sends back a reset whenever we change anything.
Okay.
And sends the values of like box size, the number of particles, and the speed, and it receives the pressure value, which is the number of wall hits. The FPGA draws everything, does all the collision detection. Am I missing out anything?
Yeah.
Counting of wall collisions,
yeah.
pressure. Yeah, so mostly everything is
I
done on the
think
FPGA.
the command line interface is just to
Interact with the user.
and also ensure that when we change a variable, the other variables that we want to hold constant are remaining the same.
Sure.
Yeah.
Okay. Very cool. Very, very cool. Awesome. Thank you both.